Assalamualaikum and salam sejahtera. First, I would like to apologize for the delay of releasing this topic. We are now at the sixth section of the compressible flow, which is on the compressible duct flow with friction. We are looking specifically into duct flow and considering the friction factor. In this topic, in the compressible flow topic, we're going to look into two external factors, which are the friction and also heat transfer. Just right after we finish the friction factors, we will look into the heat transfer in the physical lectures. First, why do we need to consider the friction? As we know that ideally we can consider the flow without friction or heat transfer, but in the real world there's no ideal case. Most of the time we will have external factors which must be considered to ensure that our analysis is as close to the actual condition or to the real world condition. We have to include the friction, especially in the long ducts or in the flow which is going through a long channel, especially when we have a very small cross-sectional area, which we know that with a small cross-sectional area we will have restriction, and this kind of restriction which we call as the friction. And for this topic we are going to look into the compressible flow with the external factors of friction, which is closely related to the wall friction of the channel. And to simplify the discussion, we will neglect for now the heat transfer in the duct, and we are going to look into the problem or into the analysis with a constant cross-sectional area throughout the flow. Okay, let us consider a one-dimensional adiabatic flow, which represent the flow of an ideal gas, and we assume that the ideal gas is with a constant specific heat or a constant Cp, and we also have here a constant cross-sectional area throughout the flow from the beginning until the end of the flow. Another name for compressible duct flow with friction is a funnel flow. I believe you have been introduced to the term of funnel flow and Rayleigh flow back in normal shock wave, which have been covered about I think 3 weeks ago or 4 weeks ago. For compressible duct flow with friction, we are considering a few equations. One is the continuity equation, which is involving the density, cross-sectional area, and velocity. As for this case, we have the constant cross-sectional area, so the cross-sectional area factors is negligible. Next, we will look into the x direction momentum equation, where we have the element of mass flow rate and also the velocity. And notice that we have the beta term in our equation, which represent the momentum flux correction factors. And for simplicity of the equation or simplicity of the analysis, we will assume that beta is equal to 1. When we look into the expansion of the x direction momentum equation, we can say that on the left hand side, which is on the force area, we have the elements of pressure, okay, shown in the diagram, before the control volume and after the control volume, and also the element of friction, which is subjected by the channel wall or the pipe wall or the duct wall. And on the right hand side we have the momentum of the flow, which consists of um, the mass flow rate and the velocity. And when we include the element of continuity equation into the x direction momentum equation, we can actually replace the mass flow rate with the rho v, or the density times the velocity, since we know that the cross-sectional area throughout the flow is constant. The actual one will be m dot is equal to rho av. Uh, we can replace the mass flow rate here with the rho v here, where next we will have the m dot times the v equal to rho v square, as we replace the mass flow rate with the rho v. And I would like to stress here that uh, the element of the cross-sectional area is constant. Therefore, we can actually divide all of this equation with the cross-sectional area. If you look here, you can see that the cross-sectional area before and after the control volume is constant. Therefore, we can call it as only A for the cross-sectional area. Now we have the second equation here, where the pressure before the control volume, which is P1 plus rho 1 V square V1 square, is equal to P2 plus rho 2 V2 square plus the friction element, where F friction is actually the force caused by the friction uh, divided by the cross-sectional area of the duct. Okay, and now the third element that we are going to look into when we talk about compressible duct flow with friction is the energy equation. Okay, since we have a control volume which involves no heat or work transfer, or we can also consider that the potential energy change is negligible, so our stagnation enthalpy remain constant. This means before and after the control volume, the stagnation enthalpy does not change. And since uh, we are considering an ideal gas with constant specific heat, we can say that the change of enthalpy is equal to specific heat times the change of temperature. Okay, hence for this case, the stagnation temperature is also constant or remain unchanged before and after the control volume. And we can represent the stagnation temperature with this expression, where the stagnation temperature is actually equal to uh, the temperature of the flow times plus the square of velocity divided by 2 times the specific heat, which is constant throughout the flow. Since this is an irreversible flow with some degree of irreversibility due to the friction itself, so there must be an entropy change, and the change of entropy is represented by this expression, where the change of entropy uh, in between before and after the control volume uh, is equal to Cp times the natural log of the ratio between T2 and T1 minus the specific gas constant times the natural logarithm of the ratio between P2 and P1. Note that the denotation of 2 and 1 in the equation is actually representing before and after uh, the control volume. 2 is after the control volume, 1 is before the control volume, meaning that before and after the process. Next, we're going to look into the equation of state as well, because we're talking about the ideal gas. So for the equation of state, the state of the ideal gas remains constant before and after the control volume. It is not the specific properties that is constant, but um, the combination of the properties where P divided by rho 1 divided by T1 is equal to P divided by rho 2 divided by T2 throughout the process before and after the control volume. This is um, based on the equation of P equal to rho RT, and the specific gas constant is remain constant or remain unchanged throughout the flow uh, before and after the control volume. Um, I did told you that the compressible flow with friction, or the compressible duct flow with friction, is also known as the funnel flow. I hope you still remember uh, the funnel line, which has been introduced to you earlier in normal shock wave. Back in our equation, back in our previous, I think 1, 2, 3, 4, and 5 equation related to the duct flow with friction, uh, we can have an infinite number of downstream states 2 for any given upstream state 1. It is quite hard to solve if you are considering a large number of variables for state 1, which end up giving you a lot of, or we can consider infinite number of solution for state 2. The practical approach is to assume certain values of T2 to minimize the variables, or to minimize the uncertainty of the solution, and from there we calculate other properties uh, inclusive of the friction force or friction factors. First, when we plot the results, the two from the equations that we have previously, the five elements, and we plot it on the TS diagram, we will have a line which we call as the funnel line. I believe you have seen this previously in the normal shock wave along with the Rayleigh line. The difference is now the funnel line is a standalone in the graph, and the line, okay, this line, you can look at this line, the purple color or the pink color, is the locus of all physical attainable downstream states. So this is the line where possibly the possible results of condition number 2 uh, can be obtained from any condition of state 1. Okay, we can see that when you look into the Mach number equal to 1 here, okay, this is the point of the maximum entropy. And when you look into the line that is representing Mach number less than 1, you can see that the entropy is increasing when the Mach number approaches 1, but it is behaving on the opposite way for the Mach number more than 1, which is for the supersonic flow. We can see that whenever the Mach number is increasing here, whenever the Mach number is increasing, you can see that the entropy is actually decreasing. Okay, for subsonic flow, whenever that the Mach number is increasing towards the Mach number equal to 1, uh, the entropy is increasing. So it's the opposite behavior between the subsonic flow and the supersonic flow. Hence we can see there are two branches here. Okay, two branches here as mentioned in this statement. For Mach number less than 1, subsonic flow, and also supersonic flow, which is the Mach number is more than 1. And okay, this is such a clearer representation on the difference between the subsonic flow and supersonic flow when we consider the friction. You can see for subsonic flow, okay, uh, look at the control volume for a subsonic flow. You can see that before and after, we will have the decrease of temperature but increase of Mach number. But for supersonic flow, we can see that there is a decrease of temperature but increase in the Mach number. Okay, and the table, this table is available in your book, the Chang'el book, uh, which is the comparison between the increase and decrease of properties uh, of the flow, the difference between the subsonic and supersonic flow. For example, if you look into the entropy itself, we look from the bottom of the table. The entropy will increase for both subsonic and supersonic flow before and after the control volume. Whereas if you look into the pressure itself, when it is for subsonic flow, uh, before and after the control volume, you can see that for subsonic flow we will have a decrease of pressure, but for supersonic flow we will have an increase of pressure. There is some kind of difference between the subsonic and supersonic flow when we consider friction in our compressible flow. Okay, now we are going to relate the properties of um, the five equation of five elements which we have discussed previously for this final flow. Um, let's look first into the continuity equation. Sorry, I started with the momentum equation slides. So we go back and we look into the continuity equation, where we have the differential form of the continuity equation equal to d rho divided by rho equal to negative dv divided by v. Okay, and then look into, we are using the same control volume, but now instead of looking into the control volume, we are looking into a differential control volume, where the friction force is actually a differential force. Or we can consider in a simpler term, the differential force is actually a small or a minimum change, not to say a minimum, a small change in the friction force. Or we can also represent the other differential form of other parameters or other properties to be a small change in the properties itself. So after the continuity equation, we can look into the x direction momentum equation, which start from the sum of force equal to the difference of momentum. Look at the cursor. Okay, next, um, when we apply the change of momentum or the momentum equation to the differential control volume, we can actually mm, transform the equation into this equation, where we have before the control volume, we have the pressure times the control volume cross-sectional area minus the pressure after the control volume, P plus dP, times the A. cross-sectional area of the control volume, which is equal to the AAC, and minus the friction, the change of friction force, or the differential form of the friction force, which is also equal to the mass flow rate time the velocity after the control volume, and minus the mass flow rate times the velocity before the control volume. To make it simpler, it was told earlier that we assume beta, or the momentum flux correction factor, equal to 1, and we will have a simpler equation. And next, when we rearrange the equation, okay, and we can also simplify the equation further, as what we have done previously in the earlier section when we discussed about the x momentum equation. We can obtain this equation on the right hand side, where dp plus the change of friction, or the differential of friction factor, or friction force divided by cross-sectional area, plus rho v dv equal to 0. Next, we continue. We know that based on our previous knowledge in solid mechanics, the friction force is related to the shear stress. I hope all of you still remember the term of shear stress, which is represented by tau W, and this is related to the local friction factor to find the friction force itself. Hence, we can actually represent the differential form of the friction factor is equal to tau W, or the wall shear stress, times the change of shear area. You can see that here there's another element of P, the small p, appearing in the equation. This P is actually the perimeter of the cross-sectional area. And from this parameter we develop another term which we call as the hydraulic diameter. The hydraulic diameter, as you can see here, this is the hydraulic diameter, which is for a circular duct. It is equal to the diameter of the duct itself. But for a cross-sectional duct area with a rectangular shape or a square shape other than circular shape, the hydraulic diameter is equal to 4 times the cross-sectional area divided by the perimeter. And from this equation we can transform the equation where tau is equal to the friction factor, local friction factor, divided by 8 times the density of the fluid times the square of the velocity, and the perimeter itself is transformed from the definition of the hydraulic diameter itself, where now our perimeter is equal to 4 times the cross-sectional area divided by the hydraulic diameter. And when we simplify further the equation, okay, we rearrange the equation, we have another equation which is fx divided by 2 times a dx divided by dh times rho v square, and we substitute the final term into the earlier term that we have here. We will have the next term here. Basically what we substitute is just the differential form of the friction force. Hence we substitute these terms into this term specifically. Hence we eliminate the term of area, okay, since we have the area here. And note that previously we have these elements of velocity, which is equal to the Mach number times the square root of kRt, which is equal to the speed of sound. We have ideal gas relationship, P equal to rho RT, and we have the term of rho V square equal to rho kRt ma Mach number square, and so on. We can actually develop this equation, substitute all of the information that we have previously into that equation. We will have 1 over specific heat ratio times the square of Mach number, dP over P plus Fx divided by 2 dH, or hydraulic diameter dx, plus dV over V equal to 0, and so on. This is actually the same equation as this equation and this equation, but by considering all of the relationship that we have previously developed in this compressible flow topic. And look into the energy equation. Previously we have developed the specific heat in relation to the specific heat ratio, and also we also develop the term of v square from the term of the velocity in relation to the Mach number and the speed of sound. And we know that the stagnation temperature is constant, or we can say that T plus V square divided by 2Cp is also constant. Hence we can express it in terms of the Mach number, the stagnation temperature, in terms of the Mach number, which is also constant. And remember that we have developed this relationship previously in the previous topic, and we differentiate this arrangement, okay, over we differentiate against the Mach number and rearrange, we will get this expression. Okay, this is the expression of differential form of this equation. Hence, we can develop the Mach number relation for this problem, or what we call as the compressible duct flow with friction. And we know that for ideal gas, we develop the Mach number relationship here for the square of the velocity equal to square of Mach number times kRt. And when we differentiate this, okay, we differentiate this expression, we will get this expression. Okay, when we differentiate the square of velocity and so on, we will get 2v plus 2v dv equal to 2 plus Mach number times kRt d Mach number plus kr Mach number square dt. We differentiate the velocity against the velocity, differentiate the Mach number with Mach number, and then we differentiate the same term with temperature. When we rearrange this differential form of equation, we will get this equation where 2v dv equal to 2 square of velocity divided by Mach number dma plus v square t over t dt. And when we divide all the equation, all the term in the differential form of the ideal gas relation, sorry, not ideal gas relation, it is a Mach number relation for an ideal gas. We can get another differential form. We divide this relationship with 2 times the square of velocity. We will get this form of differential equation where dv over v equal to dma over ma plus 1/2 of dt over t. And when we combine with the energy equation that we have discussed previously, we will get this expression or this expression. These two equation, or these two term at the end of this slide, the combination with energy equation, is actually the combination between this equation dv over v and the previous equation, which is dt over t, and you'll get these two equation. You can study further by looking into how does it being derived in Chengel's book. We try to get this video as short as possible, so the details will be available in the book. If you have any question, you can express your question in the Padlet just next below this video. Okay, next we have this ideal gas relation for the Funnel flow. We can also develop the ideal gas relationship in the differential form. When we have the differential form of the ideal gas relationship, which is initially dp equal to rho r dt plus rt d rho, where we differentiate the pressure in terms of pressure, uh, the terms of rho rt in terms of temperature, and the term of rho rt in terms of the density. And when we combine with the continuity equation, rho v1 equal to rho v2, or m dot 1 equal to m dot 2, okay, when we combine it with the continuity equation, which have been previously developed here, d rho divided by rho equal to negative dv divided by v, then we will get this term dp over p equal to dt over t minus dv over v. And again, when we combine it with the energy equation and Mach number relationship, we will have another form of differential equation, which is developed from the ideal gas relationship. Hence, for this ideal gas relationship, we will have another simple equation that we can straight away use to solve the problem, which is equal to dp over p equal to negative 2 plus 2k minus 1 Mach number square divided by 2 plus k minus 1 Mach number square times the dma divided by ma. Ma is the Mach number. And from here we can see that the change of pressure, or the differential of the pressure, will change with the change of the Mach number. And next, we substitute the differential form of velocity equation, which we have developed previously here, okay, which is from the Mach number relation, and another equation from the ideal gas relationship, okay, these two equations, into the x direction momentum equation, which we have developed here, okay, I think it is here, the final one. We will get straight away the relationship between the friction factor, the hydraulic diameter, and also the Mach number. So remember that Fx now is the local friction factor, and for any state of Mach number and x, which is the location of the flow, we can actually find the relationship between the friction factor, the hydraulic diameter, and the position, which in this equation is represented by L apostrophe, or considered as the critical length, which is equal to 1 minus square of Mach number divided by k times square of the Mach number plus k plus 1 divided by 2k times the natural log of this expression. And we can find the relationship or the friction factors by just using the elements of the specific heat ratio and also the Mach number. And provided that we know the critical length and also the hydraulic diameter. But that is not a big problem. Most of the problem, the critical length and also the hydraulic diameter is can be calculated, and we can find the actual length between two sections of Mach number. Okay, between two Mach number, um, by looking into the critical length of each section of the Mach number. Note that this critical length is actually the imaginary length where the flow will reach Mach number equal to 1, where at this point of all of the properties of the flow is at the critical point, and the difference between the imaginary point or imaginary length of the two Mach number will give you the actual length between the two sections in the duct, where in the flow the Mach number might be different or might change throughout the flow. So for a constant friction factors throughout the flow or throughout the whole length of the duct, we can simplify further the equation into this equation. So since we know that the hydraulic diameter is constant, if we have a constant friction factor, we can actually just use the critical length of both location of Mach number. Please again remember that this is an imaginary length, where at this length the Mach number is equal to 1. Okay, next, when we recall on the critical ratios for the compressible flow, all of these critical ratios also apply to compressible flow with frictions. So for funnel flow, we will be using all the critical ratios which is listed here. Okay, where the critical ratios is related to the specific heat ratio and also Mach number. Please note that all of this critical ratio will be given to you in the table if you require it for your calculation. So rest assured, don't worry. Uh, you if you can remember all of this critical ratio, it is good for you. But if you can't, a reference will be given to you in the table later. Okay, let us look into one example. We have a compressible flow flowing through a duct, which the length of the duct is 27 meter, and the cross sectional the diameter of the duct is 5 centimeter, and it is an adiabatic flow, okay, where there's no heat transfer in and out, and the velocity at the entrance is equal to 85 meter per second. Temperature at that point is 450 Kelvin, and the pressure is at 220 kilopascal. This is the diagram, and the average friction factor for the duct is estimated at 0.023. So the small f is 0.023. So we're going to determine what is the Mach number at the exit and the mass flow rate of the air. Okay, now we have to do some assumption, where this is a funnel flow, okay, steady flow with friction without heat transfer. We have a constant properties for the ideal gas, and we assume that the friction factor is constant along the duct. First, to find the Mach number, we have to find what we call as the speed of sound. We did not given the Mach number here just now, right? So we have to find the Mach number for the entrance. So to find the Mach number at the entrance, we have to find the speed of sound, where for this case the speed of sound is given by the square root of kRt, and we know what is k because we are given air as the substance or as the fluid for this flow. So from the speed of sound equation, we can find out that the speed of sound for this flow is at 425 meter per second. So from there we can find the Mach number, where the Mach number is equal to 0.2. Then turn to table A16 at the back of Channel book. From the table, look into Mach number equal to 0.2, and from that Mach number you can find the relationship of the friction factor and the length divided by the hydraulic diameter, which is equal to 14.5333. And if we are using the actual duct length to find the friction factor, to find the relationship of the friction factor, the length, and the hydraulic diameter, FL divided by DH, we found out that the value is at 12.42, which is less at as compared to the results of using the critical length. Hence, we know that the flow is not choke. So the Mach number is actually less than 1. So we can say that the exit Mach number here is not at the critical Mach number, or is less than Mach number equal to 1. So therefore we can actually calculate the critical length of the exit, or we can actually calculate the critical length where when the Mach number at the exit is equal to certain value, at what length the Mach number at the exit will reach the critical value of Mach number equal to 1. Therefore, for this case, we can actually calculate the critical length by using this relationship, which we have seen previously in these slides, okay, where the actual length is equal to the difference of the critical length between the two Mach numbers. We can actually find the relationship for the exit, or the condition at the exit. So to find the condition at the exit, we just have to use the information that we have obtained from the table here, and with our calculation for the actual length, and we found out that the difference for the condition is at 2.1133. And now what do we have to do is we just use back the table. We just have to find from table A16 for the value of this 2.133 for these properties, what Mach number does it correspond to? And if you look into the table, it will correspond to Mach number of 0.42. You have to do some interpolation to obtain this Mach number. So hence our Mach number at the exit is equal to 0.420, which answer the first first question. And for the mass flow rate, to determine the mass flow rate at the exit condition, first what do we need to do is we have to determine the mass flow rate, or we have to determine the condition at the inlet. And we know that the mass flow rate does not change throughout the flow. So we can use the condition at the inlet to find the mass flow rate itself. So to find the mass flow rate, we can use the continuity equation. First, by looking for the density, where we have the information on the cross-sectional area from the diameter that have been given to us, and also the term of the information of the velocity, which is also given in the question. So now we just need to find what is the density, and the density we can find it by using the ideal gas relationship. So our density here is equal to 1.703, and from there we can find our mass flow rate equal to 0.284. Okay, basically that is our discussion on compressible flow in a duct by considering uh, friction. um, I hope all of you will study the topic and look into details in your book, or you can find some other books related to the topic in the library. uh, Notes in PDF will be given just right after this video. You can read it further if you can't follow the pace of the video. You can read in the notes, and further details, further inquiry can be, can be you can submit your question in the Padlet, which will be shown, or which is available after this video, just right next below this video. Okay, hopefully you can understand. Anything that you don't understand, you can ask in the Padlet, or you can ask during the next class. See you again. Thank you for listening, and hope you enjoy the video. See you in the next class, in our next physical class, somewhere end of on next Friday. Uh, Thank you, and see you again.